continue to discuss the first section. Alright, so before state before stating a striking result on the representation problem of trigonometric Fourier series we define LP as the set of all complex or real valued functions on mass pi to pi such that the integral from mass pi to pi of the piece power is finite. For all p greater than 0. Okay? So this is called the LP space. Right? Now if one is P, okay, so if P is greater than 1, then any in particular L1, okay, with P equal to 1 is the set of all absolutely integrable functions on mass pi and over 2 mass pi to pi, okay, with P equal to 2 is the set of all square integrable functions on mass pi to pi. Alright, now with similar argument the beginning of this section. If f is in LP with p greater than 1, then f is in L1. Right, i.e. f is absolutely integrable over minus pi to pi. And then and in this case f is able to generate a trigonometric Fourier series. Okay. Right, so we now state theorem 11.4.b, which is called the Carlson-Hunt theorem. Carlson-Hunt. Okay. All right, so the trigonometric Fourier series generated by a function f in LP minus pi to pi, p is greater than 1, right, converges to f almost everywhere minus pi to pi. All right. So this is a very general result. Okay. So whenever we have a function f in LP space where p is greater than 1, then the generated trigonometric Fourier series converge to f almost everywhere. Okay. So this is good, not just for piecewise continuous function minus pi to pi and has left hand derivative and the right hand derivative at every point in this Fourier interval, as stated in theorem 11.1.2. Okay, this is good for any function. Okay, any function in the LP space. Okay. And the reason why p should be greater than 1 is because that mathematician Kolmogorov, okay, find a function in E1. Right, so Kolmogorov found an absolutely integral function whose trigonometric Fourier series diverges everywhere. Okay. Now, okay, so now as an application of theorem E11.4.A, okay, so we will prove a useful theorem for the termwise integration of trigonometric Fourier series. Okay. Termwise integration of trigonometric Fourier series right, so let f be a periodic function with a period 2 pi and piecewise continuous minus pi to pi and okay, so and let and A0 plus summation n from 1 to infinity and cosine nx plus bn times sine ns. So this one, the trigonometric Fourier series generated by f. Okay, so in general, we do not know the convergence of this trigonometric Fourier series. Okay, so in general, we just know that this piecewise continuous periodic function generates a trigonometric Fourier series. Okay, and we don't know the convergence of this trigonometric Fourier series. Okay, we don't know that. Right. So, okay, but we have the following conclusion. Then the series of pointwise indefinite integral. Okay, so which is x0 to x a0 dt plus summation n prime 1 to infinity x0 to x and an cosine nt plus bn sin nt and dt. Okay, so that we integrate with the first term. We take the indefinite integral here to include there. Okay, so this series of pointwise indefinite integral is one converges to the indefinite integral x0 to x and ft dt uniformly and absolutely on minus pi to pi, where x0 is any point in minus pi to pi. Okay, and in particular, we have x0 x f of p dt is equal to x0 a0 dt plus summation n equal to 1 to infinity of x0 x an cosine nt plus bn sin nt dt for all x in minus pi to pi. Okay, so originally we have the relationship that f of x So originally, we know this trigonometric Fourier series is generated by this piecewise continuous periodic function, right, with a period 2 pi. So we know that, and we don't know the convergence of this trigonometric Fourier series yet. We don't know that. But if we do the indefinite integral for every term, okay, in this series, to form a new series. So you can see this is a series of functions of x. So this here, this is the by the constant term, you do that. This becomes a linear function, and you can do the indefinite integral here. Again, you can see that this is a sinusoidal function again. Okay, so you do the indefinite integral term-wise, and form a new series. Okay, and the conclusion of the theorem is that this new series converge to the indefinite integral of the periodic function f. Okay, uniformly and absolutely on this one. Okay, on the whole period. Okay, and the starting point for the x sub 0 can be chosen arbitrarily, right? Say in this interval. Okay, so we can state that the integration, okay, the integration of the indefinite integral of ft. We don't know whether f of x is equal to this trigonometric series. Okay, we don't know whether or not, but we can do the integration. Then we can establish this identity here. Okay. Okay. So the proof. Okay. Again, please see the lecture now. Okay. Okay. Now a companion theorem companion theorem for the termwise differentiation of the trigonometric Fourier series can be deduced, okay, from the representation theorem in section number 1. Theorem 11.2.1. equals, okay, alright, so this is called theorem, U1.4.D, so this is called termwise differentiation of trigonometric Fourier series alright, so let f be differentiable periodic function. Okay, so that periodic function with a period 2 pi whose derivative f prime x okay, with the derivative x f prime is piecewise continuous minus pi and pi okay, so okay, so that maybe I stated in a more general term, right? Just like okay, just like in theorem 0.4.A, okay. Okay, so let f be up. Alright, so let me see. Be a periodic function. Be a periodic function. Okay. Okay, sorry. Right, I think be differentiable. I use the periodic function, stronger condition, okay? So f be a differentiable periodic function, okay, with a period 2 pi, okay, and whose derivative first derivative f prime, right, is piecewise continuous minus pi to pi, right? And furthermore, assume that f has a left hand and a right hand second derivative, right, at each point of minus pi and pi. Okay? So the double prime, the second derivative of f, so the f itself has a left hand and a right hand second derivative, okay? At each point of minus pi to pi. This is the same to say that f prime, the first derivative has left hand and right hand derivative. Okay? Derivatives. At each point of minus pi to pi. Okay? Alright, so this is the same thing. Now that is 0 plus summation and from 1 to infinity an cosine nx plus bn sin nx, right, be the trigonometric for series generated by f. Then the series of 10 wise derivatives, so that is summation and from 1 to infinity dx ak cosine nx an cosine nx plus bn sin nx, the derivative plus the derivative of a. The derivative of a is constant, right? So maybe the a here. So this is equal to 0, right? So we can omit the derivative of the first constant. A0, I'm sorry. Okay. All right. So this series of Thomas derivatives. Okay. So you can see we take the derivative of the first term here. All right. So this series converges to the average of the left limit of the first derivative and the right limit of the first derivative of f at every point x in minus pi to pi. And in particular, we have okay. So we have f prime of x equal to summation n from 1 to infinity. And so the derivative, when we take the derivative here, you see that we have an n of bk, bn, cosine nx minus an sine nx. Alright, so this is just the derivative of this, the nth term here. Alright, so we have this quantity for all x where f prime is continuous. Okay. Okay, so that so we have this companion theorem for the termless differentiation. Okay, right, and we need a stronger condition that the periodic function should be differentiable. Okay, a differentiable periodic function, and for first derivative satisfy the two conditions required in theorem EE202001. Okay. All right, and so now with okay. So proof, okay, again, please see the lecture now. Now, with the theorem, E1.1.2 and theorem E1.4.8, so we are able to answer the convergence and representation problems series. In the following two corollaries. Okay. So now we state corollary. And point for E. So this is the representation theorem of Fourier cosine series. Alright, so let F be piecewise continuous on 0 to pi, and F piecewise continuous derivative on 0 to pi. Okay. 1. The Fourier series, the Fourier cosine series A0 plus summation n from 1 to infinity, and cosine of x generated by F on 0 to pi will converge to the average of left hand and right hand limit of F at each point. At each point, x in the pi, okay, and the 2f of 0 plus at the end point, x equals 0, okay, and 2f pi minus the dependent limit at x equal to pi at the end point. X equal to pi. Okay. And the second, if f is also continuous on AB with A is greater than or equal to 0, but less than B, B less than or equal to pi, then A0, the Fourier cosine series converges. Converges to F uniformly and absolutely. On AB. Okay, so this is the representation theorem for the Fourier cosine series. Okay. the companion representation theorem of Fourier sine series okay. Can we state here? So let F be piecewise continuous on 0 pi and F piecewise continuous derivative on 0 pi 1. The Fourier sine series summation on from 1 to infinity Bn sine nx generated by F, okay, on 0 pi will converge to the average of different limit and the right-hand limit at each point x in the open interval from 0 to pi and converge to 0 at both endpoint. X equal to 0 over pi. Okay. Second, if F is continuous, okay, on AB with A is greater than 0 and B is less than pi, then the Fourier sine series converges to F uniformly and absolutely. On AB. Third point, or if F is also continuous, okay, on A to pi with A greater than 0, then okay, and F of pi is 0, then the Fourier sine series okay converges to F uniformly and absolutely. On A to pi. The fourth point, or if F is also continuous on 0 to B less than pi, and if 0 is equal to 0, then the Fourier sine series converges to life uniformly and absolutely. On 0 to b. Okay, so this is so this two corollaries. Now we will state a theorem Okay, so in section 11.6, Rewire is theorem 11.4.a to prove that Bessel's inequality in section 11.4. The Bessel's inequality in this section for square integrable functions is indeed an equality. As stated in the following theorem, this is called a Passiv's theorem. So if f is a square integrable function on minus pi to pi, and a0 plus a from 1 to infinity an cosine x plus bn sin x. Okay, is the trigonometric proof theories generated by f. Okay, then 2 is 2 times the square of the absolute of a0 plus summation from 1 to infinity an square plus b square. So this infinite sum is actually equal to 1 over pi minus pi and f of x square d of x. Okay. Now which is called possible identity. Yep. So we will see a proof of the theorem in section 11.6. All right. Alright, so now we go to section number 5 of this chapter. We will discuss the stem-Liouville problem. Okay. Up to now, we know that trigonometric Fourier series expansion is actually successful to represent periodic functions. Okay, and this representation, the success is actually due to the orthogonality of the trigonometric system. Okay, so let me state that. So the success of trigonometric Fourier series expansion of a periodic function is due to the orthogonality property of the trigonometric system. 1 cosine x sin x cosine 2x sin 2x cosine x sin x. Okay, studied in theorem 11.1.1. Okay, so and in this section we will explore other system of functions with certain orthogonality property. Okay, and to show that to show that they can be used to do expansion of functions. Okay, so in this section, so we will discuss many other systems of orthogonal functions on an interval. Right, on an interval, and developed from the Stern-Liouville problem, and generalized. So it's generalized the idea of trigonometric Fourier series expansion. Okay, so that this is the purpose in this section. Alright, so consider homogeneous second order linear ordinary differential equation of the form. Alright, so let's say that the form is P of x and the I prime of the prime plus Q of x plus lambda x of y equals 0. Okay, so the unknown function is y function. Okay. And the y function is governed by this homogeneous single order linear ODE. You can see here. And on some interval I, okay, of the real line, and the interval can be bounded or unbounded. Can be closed or open or half open. Okay, where the related functions P, Q, and R Px, Qx, and x are real valued functions on I and lambda is a parameter. Right, so lambda is a constant parameter here. Okay? Right, so these three functions are real value functions. Okay? Now, this ODE is called a stem level. It's called a stem level equation. Now, if p of x and the derivative of p of x, which means that p of x is differentiable, and the q of x and r of x are continuous. Okay? Okay, so if continuous, okay, finite closed interval. Alright? So this time I is a finite closed interval, and p of x, the derivative of p and q of x and r of x are continuous function. Okay, and p of x is positive, r of x is also positive for all x in AB. Alright, so with these conditions, then the stem level equation is called regular on AB. Alright, so that suppose that the differential equation is specified in a finite closed interval here. So that p of x, p prime of x, q of x, and r of x are continuous, and the p of x and r of x are positive for all x in this finite closed interval. In this situation, the stem level equation is called regular on AB, and when together, okay, with the two separated boundary condition, alright, so A, that K1 YA plus K2 Y prime A is 0. B L1 YB plus L2 Y prime B is 0. Okay, where K1, K2, L1, L2 are given real constant. And at least least one of the two constant in each equation, in each condition, must be different from 0. Okay, so together, so we have two separated boundary conditions, and in each condition, at least one of the two constants must be different from 0, because when K1, K0, then of course, then this boundary condition disappeared. So of course, this one of K1 and K2 must be different from 0, and the L1 and L2, one of the L1 and L2 must be different from 0. Okay. So now, together with these two separated boundary conditions, then a regular stem linear equation on AB, okay, becomes two regular stem linear problem on AB. Okay, and which is an example of a boundary value problem. Okay, we have learned techniques to solve for ordinary differential equations in previous semester, I believe. So let's especially to solve for boundary value problems. Okay. Now we will say that here a regular stem linear problem on AB has a trivial solution, y, which is identical 0 on AB. Okay, so you can see if y is 0, so you can see it satisfies this stem linear equation, and if y is 0, it will satisfy both boundary conditions 0, 0, 0, 0, right? Okay, so a regular stem linear problem has a trivial solution. Okay. And any non-zero, okay, so any non-zero solution of the problem call an eigenfunction of the problem, and the corresponding parameter lambda for such an eigenfunction Okay, so the corresponding parameter lambda, okay, for such an eigenfunction to exist, okay, is called an eigenvalue of the problem. Okay? Which says that for some proper value lambda, or some value of lambda, that there is no zero solution. Okay, there is no zero solutions. But if we do have nonlinear solutions, then the corresponding parameter lambda will be called eigenvalue, and the nonlinear solution will be called the corresponding eigenfunction. Okay. Okay. All right. Let's take an example first. Right, so we consider a regular stem level problem on 0 to pi. Okay, so which is y double prime plus lambda y equal to 0, and y0 equal to 0, and y pi equal to 0. Okay, so you can see that. Okay, now here the interval, so we know that a is 0, b is equal to pi, and p of x there is equal to 1. Okay, and q of x is equal to 0, and I of x equal to 1. Okay? Equal 1 for all x in 0 to pi. And the total boundary condition say that k1 equal to L1 equal to 1, but k2 equal to L2 equal to 0. Okay. Okay. And we learned how to solve this second order linear ODE. some coefficient. Okay, before. Okay, so now if lambda is a negative number, okay, with no positive, alright. So that lambda is a negative number, then a general solution of so okay, so this is the equation here. Maybe we'll say this is 11.5.1. Okay. Okay, so the general solution of 11.5.1 x here is yx is equal to c1 c1 e mu x plus c2 exponential minus mu x. Okay. Then the two boundary condition okay, so the two boundary conditions y0 equal to 0 and y pi equal to pi okay, implies that imply that so you do a substitution, right? y0 is 0, so that 0 is equal to c1 and 0, so e0 is 1 plus c2, and 0 is, so when we put pi, we have c1 exponential pi nu plus c2 equal minus pi nu is 0. Okay, and so we have two linear equations. Okay, with two unknowns c1 and c2. And so we can establish a linear equation. So we have 1 and e pi nu, e minus pi nu, and c1, c2 equals here. Alright, so we have this is a system of linear equations. Alright? Now, because the determinant of this matrix is non-zero, okay? Now, since the determinant is equal to, which is non-zero, so that 1 e pi nu, e minus pi nu is invertible. Okay? So that the solution C1, C2 is the inverse times 0, 0, which is 0, 0. Okay? So from here, we know that so we have no non-trivial solution. So we have no non-trivial solutions. Okay? For this case, when lambda is a negative number, okay? Now if lambda is 0, then so when lambda is 0, so we have y double prime equal to 0. Okay. Then a general solution of 11.5.1 x here is y of x equal to c1x plus c2. So it's a linear function because the second derivative is equal to 0. Okay, so we have that. Then the two boundary conditions. Y0 equal to 0, y pi equal to 0 implies that so y0 is 0, 0x c0 is c2 and 0x c1 pi plus c2. So this implies that c2 is 0 and c1 is 0. Okay. Alright. So that there is no non-trivial solution. Okay, for lambda equal to 0. Now for lambda is positive. The mean is good. Now a general solution of 11.5.1 is here. Alright. It's A cosine mu x plus B sine mu x. Okay. So this is the general solution here. And now we apply the two boundary conditions. So then y0 equals 0 implies that y0 equals 0 plus 0 is equal to A. Cosine 0 is 1, right? And but sine 0 is 0, so this is equal to A is 0. Okay? And y pi equal to 0 implies that now this time A is 0, so y pi is 0, 0 is B sine mu pi. Okay, so we have that. Okay, so now for non-zero solution, because now A should be 0 now, but we want B to be non-zero. Okay, so for a non-zero solution, B must be non-zero, so that when B is non-zero, but we have this equation so that sine mu pi must be 0, and which implies that mu should be equal to integers, etc. Okay, so that's yn x sine x. Okay, it's an eigen function of the STEM Louisville problem in 11.1.1 and 5.1 corresponding to eigenvalue lambda equal to n square. Okay, well, n is natural numbers. Okay. All right. With this regular singular problem, we find that we can find eigenfunctions. Okay. And the corresponding eigenvalue lambda must be square of positive integers. Okay, so the eigenvalue must be square of integers, and for each eigenvalue, the corresponding eigenfunction is a sine function. Okay, it's a sine function with angular frequency n here. Okay. Okay, right, so let us take another example. Okay. Because you consider another regular STEM Louisville problem 0 pi. Okay, so the OD will be the same as the previous example, but the two boundary conditions are different. Okay, so the two boundary conditions are different. Okay, so here we can see A is 0, B is pi, P of x is 1, Q of x is 0, R of x is 1. Okay, for all x in 0 to pi, and K1 equal to L1 is 0. But K2 equal to L2 equal to 1. Okay. Alright. Now there are three cases to consider. When lambda is a negative number, okay, again, then a general solution is here C1e nu x plus C2e minus nu x. Okay. And this implies that the derivative is equal to C1 nu e nu x minus C2 nu e minus nu x. Okay. Okay. Right, so then the two boundary conditions y prime 0 is 0 and y prime of pi is 0 implies that so the first one 0, so 0 is give us it's 0 nu, it's nu times C1 minus C2. Okay, alright, the first one, and the second one, when we substitute pi there, so it's 0 is nu, C1 E pi nu minus C2 E minus pi nu. Okay, so we have two equations, and this is divided by nu, because nu is positive one. So we have C1 minus C2, 0, C1 E pi nu minus C2 minus pi nu. Okay, and so now we have 1 minus 1 and E pi nu minus E minus pi nu C1 C2. Okay, so we have this homogeneous system linear equations. Okay. And when you look at here, the coefficient matrix is non-zero determinant, so this is invertible, right? So this one is invertible. So this implies that C1, C2 is the trivial solution. Okay, so that is no non-trivial solution. Okay, when lambda is except negative. Now when lambda is 0, so when lambda is 0, a general solution x okay, it's a linear 0x plus C2. Okay. It's a linear function. So that its derivative is equal to C1. Okay. And the two boundary condition the two boundary conditions y prime 0 is 0, y prime pi is 0 implies that 0 is equal to C1. Okay, so C1 is 0. Okay, so then that's y 0x is 1. Okay, is an eigenfunction. Okay, of E1.5.2. Okay, corresponding to 0. Okay? So the number is 0, the number is an eigenvalue, and the corresponding function is a constant function because only Cn is 0, so Yx equal to C2 a constant. So any constant function will satisfy the standard problem, okay, in 11.5.2, okay, in here. Alright, so when lambda is 0, we have a non-trivial solution, okay. Right, so this is a constant function, okay. Now when lambda is a positive number, then a general solution x a cosine x plus b sin x. So this implies y prime of x equal to minus nu a sin x plus nu b cosine x. Okay, so this is the, and the two boundary conditions. Okay, and y prime 0 is 0, and y prime pi is 0. Implies that when you do the substitution 0 here, this is 0. And so we have 0 is nu b, and okay, nu b. Alright, so this is the first one, and nu is positive, so this is implies that b must be equal to 0. Okay, the other one is 0, well, x equal to pi, so that we have minus nu, and so b is 0 really, so we have a and sine nu pi. Okay, right, and to have a non-zero solution, because b already 0, so to have a non-zero solution we must have a not equal to 0, a not equal to 0, alright? So when a not equal to 0, this implies that the sine nu pi is 0. So this implies that nu should be positive integers. Okay. Okay. So now we have yn x equal to cosine nx. Okay. X. So we have an eigen function corresponding to eigenvalue lambda equal to n square. Okay. Okay, so we have eigen function, constant function, cosine functions. Okay. And the corresponding eigenvalue are 0, the square of n square, and n can be from 0, 1, 2, 3, etc. Okay. So you can see that even though the differential equation is the same, but with different boundary conditions, you can see the corresponding regular string variable problem might have different eigen functions. Okay, as you can see that. Okay. Right. So we will consider. So recall that a truth space so space B is the set of all square integrable functions on finite cost interval AB, i.e. Okay. And we know that, as we have shown before, any piecewise continuous function on AB is a square integrable over AB, i.e. in A2 space. Okay. Now, for any f and g and two functions in the L2 space, we have the S value of the product is this and equal to the average of this sum. This is found that the arithmetic average is equal to geometric average. Okay, so you just think about that alpha okay, so this is the arithmetic average and this is the geometric average. So this is our beta, okay, for all alpha greater than 0. Okay, so we know that greater than or equal to 0. Okay, so alpha here is just the f value of f of x, and the beta is just the f value of g of x. Okay, so we have that. This is for here. That arithmetic average is equal to the geometric average. Okay, so from this inequality, this is good for all x in AB. Okay, so that when we evaluate this integral, the integral is the f value of the polar of f and g. Alright, so you see here, this is equal to divided by 2, and which is finite because that f is in L2, g is also in L2, so this integral is finite, this integral is finite. Okay. And for any complex or real constant alpha beta, we have AB alpha f of x plus beta g of x. Okay, so we consider the square of the f value of the linear combination, and so this can be written down. The square of the f value of alpha AB and f of x square d of x plus 2 alpha beta x value AB f of x g of x dx plus beta square AB g of x square dx. Now, because f and g are in O2, so this one is finite, this is finite, and we also prove that this is finite, so that the sum is finite. Okay, so this implies that alpha f plus beta g is also in L2, AB. Okay, so that linear combinations of two functions in L2 give us another function in L2. Okay, so this implies that so we can do linear combinations of functions, okay, in L2. And so that we can regard functions in L2 as vectors, okay, and we can check all the axioms for a vector space are satisfied. Okay. Alright, and by checking all axioms for a vector space, we can show that L2 occurs X a vector space over C for any positive continuous function, so positive continuous function R of x on AB, define a function for a pair of functions in R2. So define this as AB x L of x and G of x bar dx. Okay? For all f g in R2 space. Well, so we define that. And this integral is always exists. Okay. So we define that. Okay. And now, so we have to check that this integral always exists. Okay. Now, since R is continuous on a finite cost interval, AB. Okay, we know R of x will be this equal to n for all x in AB by the extreme value theorem. And then that at Rx, f of x, g f of x bar, those value is the same equal to n times f of x and the g of x bar.